In section 4, we're going to be looking at more antiderivatives, but in the previous section, we were only able to do basic power rules, their E function, our ln function. And so for this, we need some more rules or techniques in order to handle finding the antiderivatives, such as our chain rule or our quotient rule from previous derivatives. And so you'll notice that this here is our chain rule. Whenever we were doing derivatives, we would basically work from the outside in. We would move the exponent out front, subtract 1 from it, times the derivative of the inside. And so if we are trying to undo that derivative, then that means that integral is going to look like that, and we need to figure out this original function that it started with. So we need some kind of method or way in order for us to do that. And so what we do is we use substitution to help us with that. And typically you're going to see through different videos or lectures is a U substitution. So what you do is you pick the inner function, whatever you think it may be, and you let U equal that function. You come over here to the side, you take the derivative of U and get whatever it may be. And then that gives you a way to sub back into the function now for that inner function and this outside derivative. And you're just looking at now the derivative of u du. You can work out that simpler problem and then revert back using your key over here. And so that's what you're going to see in this lecture is us using the substitution method in order to undo some of the chain rules that we did in other derivatives. So here's a nice little yellow box the text gives you. It says the goal is to turn there's your chain rule, into a U substitution where f of u is much less messy than f of g of x. So let u be some part of the integrand. A good first choice is one step inside the messiest part. Always choose something that's being raised to a higher power, whatever's under the square root, possibly what's in the denominator. It says pick your u. So we're going to, step 1, we're going to pick our u. We're going to compute du and then translate all of our x's into u's. After we do that, we're going to integrate the new u integral and then substitute back in for x's. And so this is going to be the concept that we kind of focus on and practice. And I really think all these words are fine, but I think your examples are really going to see where our pieces are. And so I just want to work a lot of examples for you and hopefully show you as we go. Now I am going to color change on you and use red and blue ink to kind of help you to sort out what we're dealing with. And so what I'm going to do is let me just go ahead and rewrite this for the sake of this kind of colors to see what's going on. So faced with a function like this, all of our previous rules from the previous section are not as beneficial for something like this. I can't just jump in here feet first and go, oh, let me do some algebra first, or let me change that to a 1/2 and let me add to the exponent. So what we're going to do is we're going to pick the inside of the messiest part, or I always like to pick the part that's maybe under the square root. So let's pick this piece here. And we're going to let this equal u. Now, once you have this equal to u, you don't want to look at, and so I'm going to scan over here, you don't want to look at the rest of your problem. We picked u to be 4 minus x squared. I'm going to find that derivative. Its derivative would be negative 2x dx. Once you pick your u and take the derivative of it, then go back over here to the problem and start figuring out what you can substitute in. So we can see that 4 minus x squared, we picked that purposely to be our u. And then we see we have an x dx we need to sub back in for, which is right here, but it has an extra negative 2 on it. Now manipulate that to get the exact substitution that you want. So I'm going to divide both sides by negative 2. So I have a negative 1/2 du equal to x dx, and that will be the substitution for just x dx. And that's why I encourage you to maybe cover up the problem, or why I scrolled over to the right. Because if you're looking at your blue writing as you're doing the red, you may not see the manipulations you need to make it match up and then miss that in the process. So now I'm going to rewrite it as u. So I have the square root of u, and then x dx was that negative 1/2 du. And from our previous conversations, we looked at where if you have a coefficient on your integral, you can just move it out front, and in this u substitution, that's where it comes in handy. So I'm going to go ahead and now work with this. So this would be u to the negative 1/2 du. So that would be add 1 to the exponent, so that would give me a positive 1/2 divided by a half. This negative 1/2 is just going along for the ride, plus c. And then I'm going to continue to clean this up before I ever go back to my x's. And so really this divided by 1/2 and multiplied by 1/2 is going to go away. So I get negative square root of u plus c. And I always want to put my equation back in the form that it was given, so going back to my square root. Now that I've simplified it up as much as I can, I'm going to revert back to x's. I know u to be equal to 4 minus x squared plus c. And so you can see, once I switched it into red writing, the calculus worked out really nicely, and then I reverted it back to our x's. Again, the key is going to be picking that u substitution correctly. But just like with any math problem, if you pick u incorrectly and it doesn't work out, try something else. Erase it and try again. So let's do some more. Here's our next problem. It says evaluate e to the x over this whole grouping e to the x plus 15 cubed. So again, my advice would be to pick your inner part, whatever's being raised to some power or under a root or denominator, to be it. Now, if I had come over here to the side and said, let me pick u to be e to the x plus 15, and say I picked this whole grouping. I'm going to scan over here to the side, so this is all I see. I'm just focusing on taking this derivative, and I go, oh, okay, well, that would be chain rule. And you write it, you go, oh, that's more complicated. Then just restart. Maybe you picked too much. And so let me come back in here and let's just pick whatever's being raised to the third power, not the whole third power. So du would just be e to the x dx. I just want to create my little table over here or guide, then come back over here to the problem and make my substitutions. And so I've got a substitution for underneath. I've got a substitution for here. So now I can change it back and say, okay, well then that's going to be u cubed du. And so now I can actually find this integral. And so this would be add 1 to the exponent, divide by the new exponent plus c, and clean that up. So that would be negative 1/2. Oh, let me rewrite that. So that would be equal to negative 1/2, and go ahead and move that u to the negative 2 back on bottom. And then we can convert that back to x's. So negative 1 over 2, this whole grouping, e to the x plus 15 squared, plus c. Don't forget that plus c on there. So really the substitution really helps our integrations to be simpler and not as messy, but it's all going to revolve around picking your u and calculating your du correctly. So let's look at these. Let's look at part A. Part A has this as the integral of x squared over x cubed plus 3. Now with this one, it doesn't have a large grouping, it doesn't have a square root, but this is the one where you want to pick your quotient, whatever's on that denominator, to be your u. And again, when you do this, cover up your blue writing, just compute your du. That gives me 3x squared dx. Now, I'm going to make my red match my blue when I go to my substitution. I don't have a 3, so I'm going to have to divide both sides by 3. Not only does your u substitution help you to deal with chain rule, but it also helps you to deal with missing coefficients that got absorbed somewhere else. So this would give me a 1/3 u du. So that would be 1/3. Now this is the same thing as 1 over u du, which hopefully signals you to use natural log of absolute value of u plus c. And then we can convert back into 1/3 ln of x cubed plus 5 plus c. And so we never would have thought that we were dealing with a ln problem, but using that u substitution helped us to see it a little bit more clearer. Now let's do the reverse of it. You can see this just switched your denominator and your numerator. So in part B, let's see how that works out. So this is the integral of x cubed plus 5 over x squared dx. With this one, because the degree of the denominator is smaller than the numerator, I'm going to go ahead and do my algebra and divide that out. So that would be the integral of x cubed over x squared plus 5 over x squared dx. And so that's going to simplify down into x plus 5x to the negative 2 dx. So this one, we actually don't even need u substitution for. So that would be 1/2 x squared plus negative 5 over x plus c. Just adding 1 to that exponent gave me negative 1. Dividing by the new exponent gave me the negative out front, and then I just moved it down. So you can see the placement of the numerator and denominator did make a difference in a problem such as this, because I didn't even need u substitution because that degree was smaller in the bottom. So don't forget your algebra skills as you work through this, to make sure that you're understanding that not all problems are going to be u substitution. Once you do your algebra, it could revert back to what you were doing with our previous sections. Now that we've kind of talked about substitution, and maybe not a full grasp, but as you work through those homeworks, that will help you with that. Let's look at substitution and definite integrals. So the only thing that I've added in here is now I'm going to have to evaluate at 0 and 1. So I'm going to go ahead and do my u substitution. I'm going to pick the grouping 3x minus 1 to be my u. So du would be 3 dx. I don't have a multiplier by 3, so I'm going to have to solve that 1/3 du equal to dx. So that's going to give me the integral of u to the 4th, and then for dx I have a 1/3 du. So really this u substitution only helped me to compensate for a missed coefficient, not necessarily a whole grouping with variables. But I'm going to go ahead and integrate that. So I have 1/3, add 1 to the exponent, divide by the new exponent, plus c, and so that gives me u to the 5th over 15. Now, I actually am not going to use plus c, because you'll notice with the definite integrals, that part gets subtracted away. I'm going to go ahead and revert this back to my x's, and so that would give me 1 over 15, 3x minus 1 to the 5th, and we want to integrate it from 0 to 1. Now, you'll take note that I didn't do any changing of my evaluations from 0 to 1. Some instructors, textbooks will have you switch everything into u and then just continue from there. I feel like let's just stick with the concept we know of u substitution and then revert back to our definite integrals that we know and not overcomplicate it. And so now I'm going to evaluate. So 1/15 of 3 times 1 minus 1 to the 5th minus 1/15 of 3 times 0 minus 1 to the 5th. Again, just using your on-screen calculator is going to help you and assist you with the evaluation, because I don't want you to make any little clerical errors as you go. And this should give you a total value of, let's see, we end up at 32 over 15 minus negative 1 over 15. And so that results in 33 over 15. And I would just leave that as an improper fraction. I would not run to a calculator and get that decimal. Let's go ahead and do another one of these. Use substitution and different integrals. So we have evaluate from 2 to 10, ln x to 6 over x dx. Now this is a fun little problem to do with your u substitution. So when you're picking this, you're going to pick u to be your ln x, because that's what's being raised to some power. The derivative of ln x is 1 over x dx. Now don't be fooled by this setup. This is the integral from 2 to 10 of ln x to the 6 divided by x would be like multiplying by 1 over x. So don't let that fool you, because there's just a singular x in the problem and you physically don't see that 1 over x. But in doing that, you can see that I now have a substitution for ln x and the whole 1 over x dx, and we can switch this over to u's. And so this would be the integral of u to the 6 du. And so integrating that, I get u to the 7th over 7, and then I can convert it back to be 1/7 ln x to the 7th, and we are integrating this from 2 to 10. So now evaluate 1 over 7 ln of 10 to the 7th minus 1 over 7 ln of 2 to the 7th. Again, we want to use our calculator to help us in inputting all this, and this will give us approximately 49.01. And so again, use substitution, we're just putting it with our definite integrals and then working from there. So I want you to go and try the homework with your use substitution. If you need additional assistance, please reach out to me. I'll be happy to either work with you one-on-one or write up something, create a video, somehow to kind of help you with those problems. But they are going to take time, so make sure you're working through those problems and trying them enough time to get help, not just an hour or two before the deadline.